Welcome to another episode of Coordinate. In today's episode, we'll be exploring about digital identity. And to explore everything about digital identity, there is probably no better person than dcbuilder. dcbuilder is a research engineer at World Foundation and has been one of the most vocal and strongest supporter of digital identity with the nice properties of privacy preserving, unlinkability, among many others. DC, welcome to the show.
Thank you. Thank you for having me. Pleasure to be here.
So in today's episode, we'll be breaking our discussion in two parts. In the first parts, we'll be going over the general structure of digital identity, and in the second part, we'll be going deeper into the system design of world IDs and world's implementation of digital identity. So to kickstart the first part, DC, you had this recent blog post from December where you talk about digital identity, and you have this mental model of what should a digital identity look like. What are the core components? How do you think about it? Can you walk us through that mental model?
Sure. So the way that I think about it and that we think about it at World is that in general, like you have some form of digital data that has some form of root of trust. A root of trust is sort of the mechanism that you use to attach some form of credibility to any credential or piece of information. So you can think of it as like what makes information in a passport real? Well, that would be a signature from a issuing party. Or an issuer. In this case, it would be like some foreign government office, a travel government agency that will issue these passports, and they will have a certificate authority that will sign this hash of a passport, and thus bestowing upon it trust. And so you have an issuer, you have some kind of credential, you have this root of trust. The root of trust is this whole thing, like the whole mechanism from how the issuer attaches some kind of credibility to a given credential. And then you have a relying party. A relying party is someone who is consuming either the credential directly or an attestation about this credential. And so that would be the general flow, right? And an attestation would be a statement about the information in the credential. So it could be like if the passport credential, you have the passport credential, right? A statement or an attestation would be, hey, my age is over 18. That's like an attestation or statement. And with modern programmable cryptography...
And what do you do with the attestation? Suppose I generate this attestation. Is it for giving it to someone else to verify my statement? And
Right,
does
exactly.
this attestation, is it tying with the root of trust also? Like, hey, this certificate
Exactly.
authority has signed on it, and this is the
Exactly. So the traditional Web 2 way of doing this would be to just fully get the entire credential in plain text, right? Like you get the full passport information. You have an airport terminal to check passports. It will take an image of the frontal page and it will read an NFC chip from the passport, and it will verify the entire certificate authority in the actual device against public keys that are public. So you can verify the entire chain of the certificate authority, and now you know that passport is valid and that the information is valid. And you can also get the decryption key from the frontal image of the MRZ, and you can use that to decrypt, and you can verify that, right? So an attestation would be a subset of this. Of instead of revealing the full information, you can reveal a subset. While still preserving the sort of root of trust and essentially verifying the certificate authority and that the passport is authentic, etc. You would have a way to selectively disclose parts of that information without requiring the whole thing. The scheme that I described in my article, which is the use of programmable cryptography technologies such as ZK, MPC, trust execution environments to essentially compose and build programs to allow selective disclosure and attestations of credentials without losing trust, and being able to have that be verifying but a relying party or any third party.
Two questions on this. You mentioned root of trust is the certificate authority. Does it always have, is it always a centralized party? Like in the case of passport, it's a government. But can you have something else other than government which is not centralized? Is the design?
Yeah, totally, 100%. You can, a root of trust is any kind of mechanism to bestow trust upon any piece of information, right? So it can be Ethereum addresses that hold more than one ETH, signing a transaction where it's a smart contract and you sign that you approve of some governance action, right? So hey, all addresses that hold more than one ETH, they can vote on something, for example. and that credential that is created from that vote, for example, that can be a root of trust, right? Like the root of trust is the mechanism by which you bestow trust. It can be centralized, it can be decentralized. It's just the case for that for most credentials that sort of pertain to identity in the way that we've traditionally thought about identity. Those issuers are usually centralized, right? Like, so you think of like passports, driver's licenses, university diplomas, like certification. If you want to make attestations about those kinds of like traditional identities, you would use a centralized provider to provide you the data and some way to verify that that information is correct. And in the decentralized case, I know you can have like a web of trust network where people, for example, say like, hey, this is my favorite football player, right? Like if enough people attest to someone being their favorite football player, that can be the root of trust for such an attestation, right? And you can verify that in a purely decentralized way. It's just the sort of label.
So you are supporting someone, you are giving some weight, and I am also giving some weight, and that the whole platform system is just aggregating scores for each node.
A root of trust is just the way by which like some piece of information, like where it comes from and how I should like think about it. Like who is the guarantor of the truthfulness of such a piece of information?
So it seems like there are so many ways of having this digital identity. So if I have to place, since there are so many ways, how do you want to place them? Like, how do you think about placing them in a spectrum? Are there like different feature sets? Some forms are digital, some of them check out, maybe a lot of them. How to think about this? Because in your article you mentioned about like a lot of properties. Maybe walking through that will be really great. Like what each property even means also.
Sure. I can maybe so I don't forget all the properties of an ideal identity system that I linked on. Let me just pull up my article. So to list them all one by one. So one of them is multiple issuers, multiple consumers. So this is so that like in an ideal digital identity protocol and like the way that I think about it, you should be able to have anyone issue a credential with any root of trust that they want, and anyone being able to consume such a credential. It should be fully privacy preserving, right? So like if someone wants to share just some piece of information, nothing else should be disclosed. Unlinkability. So these are like if you have two separate attestations, you should not be able to tie them to the same origin unless explicitly like wanted to by the person who is disclosing the information. You need to have good root of trust infrastructure.
So unlinkability like you might be having identity from two different systems, and you should not be using two different systems for like say voting or something like that, like to do some kind of Sybil attack.
Yeah, so let's say that no, unlinkability is more of like, let's say I use two apps and they're like quite sensitive for me. Like let's say one app is like my employer's payroll and another app is like a DeFi app. I do not want, if I do an attestation for like claiming my salary each month, for example, and then I do an attestation to sort of invest in some like kind of like regulated product, I do not want both of those attestations to somehow be able to be linked to the same person by a like third party that is just an observer. This is sort of like the notion of unlinkability. A lot of identity systems, the way that you create the attestation, like if you use nullifiers or if you use and like different kinds of constructions, there's ways to, even if it's pseudonymous, the actions are sort of, for example, like attached to one another. So for example, if one secret is leaked, you could de-anonymize all of the sets of actions that the user has done historically. This is sort of like the case for Semaphore, which was like the protocol that we based World ID v3 upon, or like World ID 0 until like 3.
In that Semaphore is like if you like disclose the nullifier, everything of the history is gone.
If you disclose
you can link everything.
If you disclose the private key or the secret that is used to derive the identity commitment, you can sort of go through all hashes of all nullifiers on chain, and you can try and see if like the hash of this secret plus some like app ID and action ID, if it matches some on-chain logs, then you could tie that to the user. If the secret, of course, like the user will have to commit the mistake of leaking their secret, but this happens, like people can like get exploited or whatever, like so you can probably get de-anonymized like if that happens, right? You still have to like query all the public logs, which there may be like hundreds of millions, but if you have a good indexer and enough time, you can do it. So the ideal scenario would be you have a way to like rotate secrets, you have a way to obfuscate the nullifier scheme in some way. In the new version of World ID, for example, we use a multi-party computation OPRF, oblivious pseudorandom functions, so MPC OPRF scheme that allows you to also like rotate secrets. So you have this sort of like notion of unlinkability. You can rotate, but you preserve other good properties such as Sybil resistance. Like if I rotate my secret, it doesn't allow me to do the same thing twice at the same time. And there's a lot of like design pieces here that are complex on the sort of like protocol side, but we can go like that. That's like beyond the point. Like the notion of unlinkability is just this. Like if I make two statements, they should not be able to be traced to the same person unless explicitly done so by the creator of the attestation. Right. The other property
we are going to the list.
I think we have some lag. I think my internet is probably a bit laggy. But yeah, like the next after unlinkability is good root of trust infrastructure. So this is mostly like a lot of traditional systems that do digital identity, like let's say like the passport standards, like I count I'm 3 of 3, which is sort of like the standard for passports. Different countries that implement this standard use different like signature schemes. They use different hash functions. Also, a bunch of these cryptographic primitives break post-quantum. So like root of trust infrastructure should be improved in general. Like how do you bestow cryptographic trust upon the credentials? Like, this technology should be improved.
One question on that is you mentioned that different countries uses different signature schemes or hash. Why is that? Like why, like shouldn't they be just following say NIST standard? Like NIST standard is probably the global standard. Like is that not the case?
I mean, a lot of these hash functions are standardized. Maybe like, or it's also a question of like when the passports were first issued, right? Like some passports that are older, they're not gonna use ECDSA because it wasn't around yet. Yeah, like they're gonna use RSA, which is an older signature scheme. For example, they're going to use like SHA-256 instead of like SHA-3. There's always these sorts of things. And then you have permutations of these. Like one might use like SHA-3 with RSA, and one might use SHA-3 with ECDSA. Some people doing the technical implementation might have differing opinions. Like if you're a cryptographer, you might have preferences for different cryptographic primitives, even if they're standards. The way that you also, for example, commit to data changes. Like the format that the data is structured in, so the structure of the document itself might change as well. Also, it changes from document to document, right? So there's no standardized way of doing this. Or like there are standards, but at the end of the day, people have choice for what they want to do. And so in general, like we need to build like better infrastructure for this so that it's like simple, secure, also sort of like future proof. A lot of the internet traffic that is happening today that is encrypted, a lot of people are keeping that encrypted traffic so they can decrypt in the future if some of these schemes break or if computing power becomes more powerful. Government traffic, right? Like or like military traffic. Some people are like trying to interfere in like comms, and like they keep the logs of the ciphertext, and when they can decrypt, they might like learn some useful information down the line. So now people are like switching to post-quantum encryption as well in a bunch of places and stuff. So this is like just part of the whole thing. Another feature is recovery, right? So a lot of digital identity systems today, there's no good way for recovering them. So for example, in our case, in World ID 4.0, you have this notion of like recoverability or account abstraction, where you can use different mechanisms to recover your account if you lose it or if it gets stolen. That's like another useful property, because a lot of digital identity systems don't really...
So you mentioned even for a stolen ID, you can recover it. Does that mean revoking the old one and like rebuilding the new one? But this isn't that the one of the like first thing people should think about, like, because people lose all these things all the time. So is there something very hard to build recoverability in general in systems?
Yeah, it's definitely hard. I mean, like you see it on Ethereum, for example, right? Like if you have an EOA and if you lose that private key, you're done. But if you have a smart account and you have some form of like recovery through friends that you can sign something, you can recover your address within like some 2-week recovery period, like graceful period. So it's something like a account abstraction, but in the context of like digital identity accounts. And a lot of systems don't really have this because, for example, if you use ENS as your identity and you have your ENS on your EOA, you're sort of still in this scenario, right? Like if you're a crypto power user and you know how to handle private keys, maybe this is not that much of an issue for you. But if you're the average person, right, you're building identity systems at scale. Like I have many friends or family members like lose phones or forget the password to their password manager or just so many things that friction. Like if you have an identity system that you're digital life relies upon in some way, or even physical life, right? Because like digital identity systems, they complement, they're useful in real life for various things. If you lose access, then it sort of like breaks the user experience a lot. Also, if it's stolen, you don't have a way to recover it either. Yeah, so that's like another important feature. Should I just keep going like through the other ones, or
Yeah, it might be good to go through each of them and maybe explain also like what are the.
So another one is revocation. So if I create a system or a credential or an attestation, I should be able to revoke it or exit the system if I want to. Ethereum is good in this way, right? Like if you ever want to exit the system, you can just stop using it. The information on the system is persisted forever, so you cannot delete state for an Ethereum address or something, or like delete its history. But technically for like privacy systems, you can engineer privacy systems in a way where this data gets deleted forever. Because a lot of private systems, the way that private systems work is that you have some form of client-side storage that you can create proofs about. So if you just delete that, you can revoke it, or you can revoke attestations as well. This is, I think, useful because people should have the optionality to leave any system they participate. At least that's like one of my principles for this. Like if something stops being useful for you, then why not just like delete everything and exit. Another thing is self-hostability, meaning that the identity system should not rely on any trusted third party to operate the system, the identity system. I should not be able to be dependent on a bank for my identity, for example. Like in different countries, you can use your bank ID for logging into government services or whatever. So let's say the bank, like for whatever reason, they like shut down my bank account and I'm dependent on that bank ID for using services, then that directly like hurts me. So identity systems should be, of course, like decentralized, transparent, like have the cypherpunk crypto values. But at the same time, they should be
So this self-hosting goes into decentralizing the root of
trust per se. The root of trust can be public, but if it's public, it should be on like a censorship resistant network. If it's not public and you have like private credentials or private data, or like the root of trust can be public, but the credential can be private, and I should not be reliant on this root of trust for being able to interact with the protocol, right? Like I should be able to have a client locally with all my personal information. None of my personal information should be sort of custodied by a third party and should be gate kept by them, right? Like I should not, for example, if let's say you have the dystopian case scenario would be like you require your ID to like log into social media, right? And the social media is the responsible to hold my personal information. Like you should not be reliant on them custodying your personal information to be able to use their application or any other application. You should just be able to have that locally and being able to selectively disclose things about yourself to third parties as you wish, without them being able to somehow revoke you access to your own digital identity. Because if it's to become like a core part of your daily life, it should be sovereign. It should be something where the individual should have control, full control and ownership of their data. That's one. And two, the protocol should be engineered in such a way where I can interact with it without intermediaries. It should be just a decentralized, censorship-resistant private system where I can interact with it without any third party being in the way. So that would be another one. Programmable attestations. So programmable attestations is something that I touched upon earlier, right? Like being able to create a statement about any kind of credential that I have. So I have my credential with information, so like passport, name, surname, age, gender, like date of birth, nationality, or like passport country, right? Like maybe nationality is different from the passport that I have or whatever. So I should be able to just selectively disclose things about me. For example, an attestation that I could make is if you subtract the date of today minus the birthday, I can get like an age that is greater than 18, right? Like that's an attestation that you're making. And you can make these like arbitrarily.
And this typical attestations are like the way to make is generate ZK proofs, right?
Yeah, I mean, for other kinds of attestations, people like there's a bunch of ways of engineering this. You can also use things like garbled circuits, which fall upon like MPC for such a thing. There's TEs, of course. Like there's different trust assumptions for different technologies, but the abstraction of a programmable attestation is the same, right? Like programmable cryptography allows you to make statements about things, and you have some kind of properties associated with that statement. The property of ZK or snarks and starks is that they're verifiable. and it's also that it's succinct. So it's much easier to verify the statement than like computing it yourself from the beginning. And also that you have privacy, right? So trusted execution environments give you privacy and verifiability, but you have a hardware assumption. But it's also cheaper than ZK when it comes to computation, right? You're computing directly on the chip. You're not sort of using math for securing the thing. For ZK, you have computational, it's more computationally expensive to create a proof, but you have privacy and you're just relying on math. You don't need to trust the sort of host device besides leaking the witness. You cannot leak your private data to a third party. So when you're creating proofs, another big thing, which also sort of would fall under the self-hostability side, is when I'm making these programmable attestations using ZK or MPC or TEs or whatever, at the end of the day, you should never have to leak your data to a third party to create the attestation. So in one of our biggest focuses at World is on client-side proving, creating zero-knowledge proofs on the devices that users control. And in our case, all of our users live on mobile phones, right? Like World app is an app on Android and iOS that has 38 million users. And one of our big sort of values is accessibility. So if we roll out a feature, it should be accessible to like the P99 user, like the 99th percentile of users. And that includes people that have really bad phones, like not good phones at all, like bad CPU, bad RAM.
Like the specs from 10 years ago. Probably.
Yeah, exactly. The specs from 10 years ago on like a low end phone. So if you want to create ZK proofs on such a device,
one question on this it's client side proving is so in mobile phones, what is the main issue? Is the RAM usage, the power, like
it's everything.
Is today's stack in a it's everything.
It's
and
everything,
is the ZK proving client side ZK? And the client-side ZK proving, is it the state where you can do this P99?
We've been working for 9 months on a new Noir backend. So Noir is this domain-specific language for writing ZK circuits that was developed by the Aztec team. So Aztec is a team building a private layer 2 on Ethereum, which is programmable at the same time. You can have private smart contracts, private state, etc. And you can sort of build smart contracts that are private. And Noir is the language that they made for this. However, Noir was not optimized for proving in mobile devices. It's definitely optimized for at least for like web proving, because most people assume that like a lot of these things are going to run in wallets on mobile, on browsers. So it's definitely optimized at least for like computers, but not necessarily for phones. One of the constraints, for example, for phones is just the size of the binary of the app, right? Like our app is already like over 200 megabytes. And so like if you have a prover, and like let's say you have like trusted setup files, right? Like if you have a proof system that is like Groth 16, you have trusted setup files, etc. Like you increase the size of the binary by a lot by just adding a prover. And people may not have data that allows them to download a big app from the App Store, right? Like that's one. Two is like what I mentioned with like RAM and CPU usage. Like the process will just die before it's able to create a proof because it's not able to keep all the numbers that it needs in memory to create the proof. So that's like another one. Then it also needs to be on-chain verifiable, right? So like the end proof needs to still be like EVM friendly. The proof time needs to be fast, right? Like the user experience cannot be slow. If you're creating a proof of a passport, you don't want to be waiting like 2 minutes idle with your phone, like being like super hot, not being able to do anything, draining your battery, just to create a proof that you're over 18 to access a website. And you have to do that every time you use the website, for example. Like there's a lot of like constraints here when it comes to user experience, when it comes to the constraint of the hardware itself, when it comes to the properties you want to have so that it's like client-side privacy, but on-chain verifiable. And so we took all of these constraints. Also, like when it comes to like how big of a circuit you need to prove under what time, using like there's a bunch of constraints from the user experience perspective that like translate into the technology design and like the sort of PRD, like the product requirements description. And so once you do like engineering from there, like from first principles, like you reverse engineer like from the goal to the thing you need to build. This is sort of like what we came to, and so we've been building a Noir backend for the last 9 months, which is optimized for mobile proving, and hopefully it should be ready sometime in Q2. Yeah, it's called ProofKit. It's open source, but yeah, like there's a lot of things that we've worked on here to make it so that you can do such a thing even for low-powered phones. At some point, we just believe that you should just get a better phone, like because like the value of the applications should sort of help for that, or at least like like if you get a modern phone that is like very cheap, it's still better than the low end phone from back then. So at somewhere you need to make a cutoff, because like it's just impossible to support like super old, super bad phones. We're trying to be as accessible as possible. Like that's one of the core values for the things we build.
So one thing, one meta question is that there can be so many digital identities, and suppose an application says that an application who wants to get as many users as possible would like to get more people, it will allow multiple identity systems to be integrated with the app. So now the problem is that many people will use these different identities to do same action multiple times. Is there a way to link all these multiple identities so that the app knows that you are not like using your same identity multiple times from different systems to access the app and do actions in the app?
There's different ways to address this. One is like protocol level, the other one is like app level. The way that most people think about this, like I'm definitely pro pluralism, because like you have more competing ideas. If something is a credibly neutral protocol, it should be agnostic. It should not bake in assumptions of the identity protocol it should use. You're building something that is neutral infrastructure for everybody to use. I believe that there you should not bake in anything. If you're building an app and you're a specific app and you're like a founder and you're building a business or whatever, you have the choice to use whatever digital identity protocol or primitive or product that you want. And if that's the only one you want to support, you can support only that one. If you're building an app that is trying to also be credibly neutral, well, then you can have some form of like ranking system. So I don't know, like maybe a good example of something that already is like this is like Gitcoin Passport back in the day, which became, I think, I forget what they pivoted into. I think it was a company that spun out of Gitcoin. I forget the name. Gitcoin Passport would allow you to do is like integrate a bunch of identity providers, and then it'll give you like a trust score. Like if you integrate like 10 out of these, you get a higher trust score. So whatever attestation you can have something like quadratic voting, right? Where like you have a weight of an individual attestation, but in the end, the thing that matters most is how many individual attestations from independent accounts are happening, right? But like if you have more identities connected to the same identity, your identity would still have higher weight in the voting, for example. And this was useful for things like quadratic funding in Gitcoin, right? Like where multiple people can vote for who should get the funding from the Gitcoin's pool, or like from the general pool of people that donated to the general pool for like a given Gitcoin round. And then you'd use that, right? So you can definitely aggregate multiple identities to create a joint score if you want to be like this like agnostic protocol that is like trying to allow anyone to use any kind of the identity that they want to use, without still breaking Sybil resistance, right? Like because you have a higher guarantee that this guy or like this girl is like a unique Sybil resistant entity in the system, the more identity protocols they have connected to one account, right? Like it's a higher weight. That's like one way of doing it. The other way of doing it is like having a web of trust kind of protocol. So for example, if you build a network of unique humans, like think of World ID, for example, you have 18 million verified users, or almost. If those users build a sort of like a social graph, and they attest to people that are not on the graph, that like, hey, this is a unique human, and like 1,000 people who are World ID verified attest to someone being a unique human, that is also like a way, like to include people who are not verified in a system that sort of has.
So in this case, the verified humans from World ID become the seed of that web of trust. Right? This seed is then supporting, hey, these are the other humans I know for this things.
And you can have multiple networks, right? So for example, I can have a network for World ID, you have a network for like ZK Passport, RARIMO, Self. There's like multiple competing parties building identity infrastructure. There's like Google with ZK Passport stuff as well. So for example, like if multiple people in these networks like attest to one entity, and you can cross-link these attestations to one entity, maybe that entity also has like a right to be like treated as if they're SIB resistant without having to have an account in either of those systems, right? So that's like another way to solve these things.
So I want to move from the digital identity to something you have been like mentioning in the Twitter, is about this private confidential state. I hope I'm pronouncing it right. So what exactly is it like? So you have the ZK already, which people think that it's a privacy and it's some kind of confidentiality is there.
Yep.
but so how is it different from this private? Like, what is new there in private confidential state?
So in confidential state, the issue that you had was that you either have fully public state or fully private state. The problem was like how to do private shared state. So just to illustrate the example of how this works is private state would be something like a Tornado Cash note. Like I deposit money, ETH, into Tornado Cash or privacy pools, which is sort of like the new flavor of Tornado Cash. I deposit one ETH into Tornado Cash and I get a note. And this note is just a secret. And then I can create a proof that I own this note to claim it to claim the one ETH from a different address. This note was private state. It's purely private. It's off chain. The note is nowhere on chain to be found. It's purely private state that is kept inside of a wallet client side. This is private state. Public state would be like Ethereum state, right? Like it's the state in a smart contract that anyone can query from any like so this is sort of like public state. Private shared state would be, for example, I have a smart account that is shared with 10 friends and only the 10 friends can see the balance. There is no way to do such a thing now. There's no way to unless you share the node with everyone, but that's maybe not something you want to do, right?
That defeats the purpose of confidentiality.
So the way to do this would be with multi-party computation and OPRF, oblivious pseudorandom functions. So essentially MPC allows you to take some piece of data, split it into shares, and if enough shares come together, they can decrypt, but also you can just compute on the shares without decrypting and only decrypting a result, right? So for example, maybe we want to figure out, like we all work at 10 companies and we have a salary. We want to figure out if we're getting underpaid or overpaid without revealing each other's salary to one another. So we can compute the average without ever like revealing our information to each other because we have these encrypted shares. We can perform the computation and just decrypt the result of the average. Hey, am I above the average or below the average?
And each MPC node is only getting encrypted shares. They are not getting the full data, right? When they are doing the computation.
So in the context of digital identity, you can have information that people can compute over, but it's encrypted information and they can decrypt the result of some computation happening on encrypted state.
How does another third party knows that the encryption happened, the computation was done correctly? Do you have some kind of cryptographic proof?
Exactly. So multi-party computation gives you verifiability baked in. It's sort of part of the protocol, just like ZK in a similar sense.
So there is a ZK element within this.
However, there are some attacks you can do in multi-party computation systems. Like I can be a node trying to run a different version of the client for the MPC, and I can be trying to like sort of snoop on traffic and stuff. For this, the way to improve it is running the MPC client in like a trusted execution environment, right? So I can prove that I'm running the public like client source code inside of a TE, right? So I'm proving like in order to join the MPC network, I need to attest with the TE that I'm running the right software, for example. There's ways to mitigate this kind of assumption as well.
And this system is called OPRF, or OPRF is a separate system?
OPRF is a mechanism that allows you to sort of query information from such a system in a private way. So I can create a query to this private state without learning anything else, and like the query itself is private.
So basically you can't even know that what I queried. That kind of trace leakage is going away. How does that work?
Yeah, I'm not a cryptographer myself, but I can just give the sort of like Gemini explanation for what OPRF is. So OPRF is a two-party cryptographic protocol where a client with an input X and a server with a secret key K jointly compute a pseudorandom function. The client learns the output, but not the key, while the server learns neither the input nor the output. So essentially, like whomever who is calling a function inside of this like MPC OPRF system, the client who's doing the query with any input, they learn the sort of output of applying a function on a secret, but they don't learn the secret, and neither does the server doing the operation. The server doing the operation doesn't even learn the input that the client is using, right? So essentially imagine if you have a server, the server is able to serve a client without learning what the client is doing with the private data. So this is sort of like the property of OPRF. So if you have private identity state, And let's say like a user is trying to make an attestation about some information that needs to have like liveness, right? Like the information needs to be sort of trustless and in a decentralized network. It should not just be reliant on a single person to custody the state because it's like important state. And the person can make a query of their information without the server learning what that information is, right? Like you can build decentralized networks that keep private data from third parties. They can help with liveness, right? Like there's multiple computers keeping this network alive through like crypto economic incentives. This would mean like proof of stake or whatever, right? Like you have a network of nodes or MPC nodes keeping state together, and any client can query this network for information. They can make computations on it too. Nobody, including the servers themselves, can learn what this information is or what computation happened. They're just doing operations on top of the MPC encrypted state, and the way through which this data is queried is also private.
So it seems like there is a very good applications you can do, like voting, for example, where the server can't even know like which candidate you voted for. Some kind of confidential voting you can do.
Yeah, confidential voting is like one of 100 things. You can do any arbitrary, like imagine you can do like private finance, you can do private computations of any kind, right? Like any kind of data processing, information processing, identity processing. You can like compute information on verifiable but private state without revealing anything.
Let's move to the second part, which is about the architecture of world, how world is implementing. So one of the questions I have seen many people asking is that about privacy preserving of the world orb. Can you explain that what like for the orb, for the iris orb, how does it work? Like how is it maintaining privacy?
This has multiple components. So if you start with the hardware, right, the orb is custom hardware that is made by Tools for Humanity, which is like the founding entity of World, or the labs entity, if you want to think about it that way. The orb has multiple components, right? You have the operating system, which is a NixOS, like Linux-based system. The operating system controls different chips that are on the device, including a trusted execution environment, which is part of the NVIDIA GPUs, which are embedded GPUs. I forget the latest NVIDIA embedded GPU that we use, but the previous one was the Xavier Jetson NX, which was like the state-of-the-art like 3-4 years ago for embedded GPUs. And this GPU has a TE built in. So a lot of the confidential processing that happens of like, for example, the machine learning models that create the proof of liveness and proof of uniqueness, they happen in an encrypted way in the trusted execution environment, and you have a hardware assumption there. So that's how you have like privacy on the level of the actual like orb itself. The orb itself also doesn't keep any information. So when you go to the orb, you download World app, you show a QR code to the orb, you get verified, as in like you stand in front of the orb for a couple seconds. It will prove that there's a real human being in front of it. There's like the infrared camera, and an RGB camera, time of flight camera, a 3D depth sensor, a sort of heat sensor. So you have information such as, hey, the person standing in front of the orb has a 3D face which with a heat map that matches that of a human being. They're not wearing contact lenses, glasses, because there's machine learning models to detect that as well. They don't look like a child, right, because of consent. So there's models that detect that as well. And so that's like the liveness part, like you prove that there's a real human being. After that, the orb will take a high resolution image of your face and irises, and the secure enclave of the orb has a private key which will sign the images that it took, and it will then store them on the user's device. After you have these signed images, the orb essentially will prove that the images that it took are from a real human being. It will bestow cryptographic trust. It will create a root of trust, right? It will sign it. That's the root of trust. And also the orb is made to be unspoofable. So this is sort of like the thing that gives the root of trust legitimacy. Also the SD card on the...
So here the orb is the certificate authority.
Exactly, yeah. Correct. Okay. Well, and also we're like doing work to make this like more publicly auditable, so you can have like an on-chain registry of all the public keys of all the secure enclaves for the orbs that have signed things. Because as you decentralize, right, you can think of like having third parties that manufacture their own orbs, right? And they should be able to also insert or like create like proofs of personhood, right? Like, or insert people into this identity system.
And what happens to the data that the machine learning model is doing for scanning the iris? What happens to the data after you have locked your phone with that?
Then it's deleted. It's fully deleted. The orb doesn't even have like disk storage. There's no place for it to store besides memory. And after the process ends, the memory just gets freed. So there's no information that gets left over. The only thing that the user then has is an image of their face and irises that is locally stored. We call this the personal data custody package, or PCP, and it's a signed set of images. And then what they do is they create a iris code locally. An iris code is a vector embedding of the randomness of the irises. You can think of it as like the entropy. It represents like the uniqueness of the iris, right? And each iris is unique for every human being. And if you combine these vector embeddings, you can compare the distance between these embeddings in multidimensional space. And if the distance between a pair of embeddings is greater than a threshold for all the other embeddings, for all the other uses that have been verified, then the user is considered unique. The original system didn't encrypt these embeddings. So the embeddings themselves are not PII, as in like they're not person identifiable, but they're derived from, so they're still sensitive information.
So,
but the way that it works now.
Yeah, so I was asking the vector embeddings, right? They can still leak the data, right, of the original image.
They don't leak the data of the original image, because you can think of it like you go from like a high resolution image to 12,800 bits. Even if you have the computation, you try to upscale back, you don't have a way to get back the original image, but you still get some features because it's not total information loss, but it's not enough to like know.
So this is like some kind of PC, a principal component analysis you're doing, going from high dimensional data to this low dimensional data and storing that part.
The way that you get there is with this thing called a Gabor wavelet. A Gabor wavelet is an ensemble of Gabor filters. You can think of it as like a filter which sort of like a Gaussian, like it's strong in the center and like then it fades out. And then you have this like sinusoidal function, which is sort of like you have this like factor lambda, and the lambda sort of makes the sinusoidal either like big or small. And so you can have different sizes for the actual like Gaussian, and then different lambdas so that you can check the frequency of the sort of like sinusoidal function. And so once you create an ensemble of these filters, so like filters that have a different Gaussian size and a different lambda, you can have like 28 of these. And if you apply these 28 filters on the original image, you get the iris code, which is like a sort of like a result of this convolutional like operation that will create the representation of the randomness. It's sort of like a low dimensional space, as you mentioned.
So you transition to frequency domain with the Gabor filters, and that's where the operations are happening in the convolution operations.
You get like this iris code at the end, and this iris code has enough like information to encapsulate like the randomness, like the random bits that it has. And if you compare the overlap of these random bits after performing this sort of like downscaling operation to the iris codes, and you also do an AND operation because you have left eye, right eye, right? So like if you only had one eye, there's less randomness, right? But like if you have one eye and the other eye, you have like double the randomness. And if you do the AND of like left and right, and you compare left and right against left and right for all the other vector embedding pairs, you have this operation called the Hamming distance, which is like similar to like the root mean squared error. Like if you think of like the distance across this it's like similar to that. You compare the Hamming distance for all the pairs of iris codes, and if the distance is greater than a threshold, you deem this person to be unique in the system, right? And the design of this system needs to scale for billions of users. That meaning that even if you add like billions of vector embeddings in this like space, in this vector space, the probability that you're going to collide against someone else when you're a new entity is really, really small or impossible, right? Like you should not be able to collide against someone who is in the system while you are a new user, right? Like this is like the hard property of building such a system. And this is called a false positive, where you have a false match against someone in the system.
Yep.
And false non-match would be that I am not a unique user, I'm already in the system, and I get a new ID regardless, right? So if I go to the orb twice in a row and the orb gives me two different identities, that's a false non-match. The whole goal of the biometric side of world is how do you minimize false matching rates and false non-matching rates, even if you have like 1 billion or 10 billion identities in the system. This is like the main sort of problem that the AI and biometrics team at TFH have, right? Like how do we make sure that one, the liveness proof is as robust as possible and nobody can fool it, right? On the biometric side, of course, there is like attack surface area on the hardware and firmware side. But once it passes hardware and firmware, the biometrics team is concerned on like the biometrics attacks vectors, right? Like making sure that nobody can spoof the image or try and fool it so that like people can pretend that they're real when they're not. And the second one is the uniqueness side, right? Like the resolution of the iris codes needs to be high enough so that you can tell apart two individuals at scale in a way that is also privacy preserving. And then once you have this like uniqueness check, the person's sort of identity commitment, which is sort of like a public key derived from the secret that World App generates on download, or like when you create a World App account or World ID account, you have a secret and then like a public key derived from the secret. We call it an identity commitment. Once you get verified from the orb, you get your identity commitment inserted into the set of verified users, and you can use your secret to create a ZK proof that you're part of the set of verified users without revealing which one you are.
When you say using ZK for proving that you are part of the group, verified ID group, so is it like generating a ZK proof of some kind of Merkle tree?
That's like Semaphore v3, which is the previous version. So it's just the Merkle tree of public keys. You can think of it as that. The zero knowledge circuit is essentially verifying I have a secret that, if hashed, gives me one of the public keys in the Merkle tree, and I have the Merkle path for my public key. So essentially, I supply the Merkle path, the secret, and the circuit will have the secret as a private input, and it will hash this private input, verify that the private input, when hashed, gives you the one of the public keys in the Merkle tree for which I have a Merkle path for, or Merkle proof for, and then it will create this proof that, like, hey, I own a secret that, if I hash, belongs to one of the identity commitments in the tree, without revealing which one it is, and I make this proof that I'm a human. This is sort of like, you have the root of trust, you attach the root of trust to one of this like public keys, and then you prove that you own a private key, you own a public key without revealing which one you are. That's like how the trust carries over to the end attestation. One thing that I didn't mention was the way that these iris codes are checked against each other is also an MPC. So you use multi-party computation for checking these iris codes against each other. They're stored as linear secret shares across multiple parties. And in our case, these parties are credible, like third parties, like neutral third parties, such as universities, regulating authorities, like regulating bodies or regulator bodies.
So two questions on that. When you mentioned that like there's a circuit running to generate that Merkle, the ZK proof of the Merkle membership. Is it running in the client side on the mobile phones? Is that exactly what's happening?
Correct. So when you're creating World ID proofs, you're running a ZK proof locally.
And the second one, you mentioned that you use MPC for the distance check among the iris codes, and it generates the iris code of my iris. Does it get distributed across the multiple MPC nodes? Is that what's happening? And then it does the computation in an MPC manner, and that it gives back the output, that is it in unique human and all this thing, the new ID.
But you split the iris code locally on your phone, right? So you just create locally like these linear secret shares, and you send them off to the nodes, which then can like perform the uniqueness check against all the other ones. And if they pass the uniqueness check, it will insert the sort of like MPC split iris code into a database on this MPC network.
Given that you have all this system, what is the world rollup doing exactly? Is it for storing some kind of information of this biometric ID? How do you guys think about it?
World App or World in general is trying to become the largest identity and financial network, and so every user on World App also has a wallet, like a safe smart account. So if you have a safe smart account for every app, like when you download World App, you get a safe smart account. And this safe smart account is deployed on WorldChain for every user, right? And also a big part of like how we originally bootstrapped the network was by giving a share of WorldCoin to every single user. So where the user is creating these zero knowledge proofs and verifying them on chain to claim a monthly grant and also a grant on sign up. All these things, for example, happen on WorldChain. Also, we have this thing called mini apps. So every single World App user can interact with third-party applications. So you can think of it as like a different app store where Polymarket and Kalshi have built mini apps. And the users of World App, they can use the World App wallet, which is a Safe Smart account, to interact with like Polymarket and Kalshi through their World App balances as a mini app. And these mini apps are deployed on WorldChain, right? So the way that they get access to these funds is like to an EVM smart contract that is deployed on WorldChain, right? So anyone can deploy any smart contract and build an application that lives on WorldChain and target World App users. And it has native support for things like the World ID. So like you have this mini kit, which is the SDK for building apps on World App. You have direct access to things like World ID, to things like payment APIs, like triggering safe smart account transactions for paying with a token or for interacting with a smart contract. All these features are natively integrated and vertically integrated. So this is the reason for world chain. Like if you have tens of millions of users doing transactions that are financial, you need to have a way to scale that. And that's why we chose to go with a custom like L2 that's based on the OP stack, part of the superchain. And so originally we were on Polygon. This was in 2021. Then we migrated to Optimism. This was pre 4844. This was in 2022. And then we launched WorldChain, I think, end of 23 or beginning of 24. I don't remember. I think it was October 24 is when we launched WorldChain. And mostly it was because of reason of cost. Like we were consuming like 60% of Optimism mainnet block space. And so we were running out, so we needed our own space. And then thankfully, like all the DA improvements, like peer DAS have come, and like blobs are much bigger. There's more of them. So like now it's a lot cheaper, but back in the day it was like an existential thing because we're subsidizing all transactions that happen on World App. All transactions on World App are free for all users. So we were like raking up quite a big bill on like gas fees on originally Polygon, then Optimism mainnet, and then WorldChain. But World ID itself, to answer your biometrics question, World ID itself has the Merkle tree currently on Ethereum mainnet. And for the next iteration, most of the infrastructure will be on WorldChain as well, like the smart contract infrastructure. And there will be bridges from WorldChain to other places as well. Because the goal for World ID is to be a credibly neutral and trustless system. So you can technically use World ID on like Starknet. There is a bridge that was recently deployed by Nethermind for Starknet. And now you can use World ID on Starknet and verify World ID proofs on Starknet. And there is an app there's a prediction market called Olena that already like uses that on Starknet. There is also, for example, a bridge for Solana. It's not used in production, but there is one that is built. There's bridges for all the OP stack chains that anyone can deploy if they want to. We're also working on integrating more over time, like building more bridges, because now we're sort of at a point where we can scale this out more. And we're coming out with a new version of World ID, which is World ID 4.0. And so we're also building like new bridges for the new version of World ID so that it's like available in multiple places at once.
So I want to move to this question next is, what do you guys think about identity for agents? You guys have been working on identity for humans, but how do you guys think about the model for identity of agents? Because agents will be like they're spawning everywhere in the internet, so it's a big issue also.
So there's not much I can share yet. We're working on a blog post on this. So like once we release that, you can just read that. But we're definitely working on it. Like there's a lot of real use cases for which I agents, and also like agents that are controlled by a human. Like you really care, like if you have a robots.txt and you're getting scraped by like Google or OpenAI or Anthropic for like whatever, like these kinds of agents can feel they're not really useful because they can be bots that are just querying your website for information to bypass your API or something, right? Like for example, like I want to get all tweets, but the Twitter API is too expensive, so I just create a bunch of scrollers. The crawlers will create X accounts, and then they will try and fetch data from X accounts, for example. Right, but if you have a unique human and you associate a unique human proof or proof of human to an agent, that agent suddenly becomes more trustworthy to any app, whether it's a user or an agent using the app through the UI or an API even, right? Like even if I have like, I don't know, like the Stripe API, and I have an agent using the Stripe API, if the agent is verified that like, oh, it's only one agent owned by one unique human, that agent suddenly can get preferential treatment on the API because like it costs Stripe money to process like these requests. So you can do things like higher limits. Like let's say that you have a free tier for like ChatGPT or Anthropic, like Claude or Gemini or whatever. You can have also like a higher free tier for these agents, right? Like if this agent calls my API for like getting access to, I don't know, whatever information or something, or do a query and use a tool or something, whatever. If you associate proof of human with it, that's like really useful. So we're definitely building infrastructure that allows like a bunch of these use cases. And eventually my whole like idea for how this is going to happen is it's not just going to be proof of human that is going to matter for these agents. There's going to be a financial identity, right? Like there's going to be like money, stable coins, tokens that are going to have like these agents are going to have access to with some policies, like spending policies for this agent can interact with this smart contract and spend so much, so and so money based on these actions, whatever, that I create a policy for this agent to interact. but they're also gonna have like the traditional identity, right? So like I care that this agent is owned by someone who has done X, Y, and Z things. Like there's someone who has, like, I don't know, been to an event, or like you can do like a POAP ZK proof. You can do this financial, like this agent is owned by someone who is financially literate, and like you can, for example, prove that like they've had more than $300,000 of a borrow position on Aave for longer than 3 years with an over collateralization ratio of like 3. You can prove things like reputation, like preferences, like who you are, like selectively disclose things that have a root of trust. For Ethereum stuff, you have a complete root of trust for all Ethereum smart contracts because the Ethereum tree is Merkleized, right? You have the Merkle Patricia tree. Although that one will probably get replaced with like a Verkle tree or something else, but you still have a root of trust that is verifiable. You can do an inclusion proof of Ethereum state against the root tree. And if you call that one, you get a full like Merkle Patricia tree proof of the inclusion in tree, and you can use like a ZKVM for verifying this. And then you have a full proof of inclusion of state in the EVM. For things outside of the EVM, or of Ethereum or any Merkleized database, you have to do the full like root of trust verification pipeline, and then the selective disclosure of the statement, and then you associate the statement with like an agent, for example, and then the agent can do whatever on your behalf, or on anyone's behalf, right? Or it can be a self-sovereign agent too, but that has an identity on its own. And for example, if the agent is like GPT 5.4, there's another agent that is like 4.6, like Opus 4.6. And now that you have these two agents, you can, for example, have them trade, and the trades that they've made is part of their identity. Now this agent can prove that like, hey, I'm a self-sovereign agent. I can create a log of all the like queries that I've done to the API, and like the API can have like an attested TE, for example. Like I've actually fetched this information from the Claude API, like Anthropic or OpenAI APIs, and I can associate this attestation together with all my transactions. And now I can, like, this agent actually has an identity now, right? You know, like I'm proving that I'm getting all my information from the Anthropic or OpenAI APIs, and that I've made trades that are profitable, for example. Like this can be like a self-sovereign thing too.
I think this is a right place to end today's episode. So I just want to summarize before we finish today's episode. We talked about two parts. In first part, we talked about the whole general structure of digital identity. What does an ideal digital identity even look like? And in the second part, we talked about the world's implementation of digital identity. And really appreciate DC for going through both of them. And I'll highly recommend everyone to read the blog post that DC has written. It is really good as a starting point, and you can then have the links that DC has put there in the blog to go and dig deeper.
It was a pleasure talking to you. If you want the links for the listeners, it's dcbuilder.dev/blog, and it's the latest blog currently. The Future of Digital Identity Part 2. And for world stuff, the sort of like entry resource that I would recommend is the white paper. So whitepaper.world.org if you want to learn more about any part of the protocol.